let's interpret this result. Now, first of all, f of xy is, we call our acceleration, which is uncertain because x and y are regarded as uncertain. X is 3.6 seconds plus or minus an uncertainty of 4 seconds. Y is 30 centimeters plus or minus an uncertainty of 2 centimeters, which gives us an f of xy, an acceleration that's uncertain by 0.9 units. Now that's going to be centimeters per second squared, but we're not going to worry about the units. So what is our acceleration based on our x naught y naught point 3.630? Well, if we plug 3.6 and 30 in, we get this, and I believe 3.6 squared is close to 13. That's 60. 13 will go into 64 times remainder of 8, which is a little more than half of 13. So I'm going to say 4.6 plus or minus the 0.9 we've got here. Now, all these calculations I've done mentally, and they're not going to work out perfectly, and I, as usual, expect that you'll kind of work through the calculations and think about what they mean and get the correct results. But in summary then, we have A is 4.6 plus or minus 0.9. 0.9 is 1/5 of 4.5, 1/5 is 20%. So I'm saying that we've got about a 20% uncertainty in our value of the acceleration. That's based on our differential analysis. Now, our plus or minus in our value of y was 2 out of 30. 2/30 is 1/15, which is about 6%, actually closer to 7%. But we'll ballpark that figure. It's 6 2/3%, so it should be 7%. Let's fix that by saying that's about 6.6%, and repeating, fudging a little bit, it's about 7%. Okay, 4 goes into 36 9 times, so this is 1/9. 1/9 is about 11%. So we have about a 7% uncertainty in our value of y and about an 11% uncertainty in our value of x. And according to our analysis, that leads us to a 20% uncertainty in A. Now I'll tell you, we should get closer to 30% uncertainty, so I've probably got an error in the calculations. We might review those. In any case, we also obtained the expression for delta f, fx delta x plus fy delta y is negative 4y over x cubed delta x plus 2 over x squared delta y. Now, our uncertainty as a proportion is delta f over f. Remember, we divided our delta f, which is 0.9, by our value of f, which is 4.6. So we did delta f over f, then we converted that to a percent. This would give us our uncertainty as a decimal, but that's easily converted to a percent. What is delta f over f? Well, delta f is the expression you see here, negative 4y over x cubed times delta x plus 2 over x squared times delta y. If we divide that by f, well, we're dividing that by 2y over x squared. What's that? Well, we're going to multiply through here by x squared over 2y. X squared into x cubed is going to leave us an x in the denominator, and a 4y over 2y is going to give us 2. The negative sign will persist. We have negative 2 over x. Multiplying this first term by the reciprocal of this denominator, we should get negative 2 over x, and that's times delta x. And very similarly over here, multiplying by the reciprocal of the denominator, we'll have an x squared over x squared, and we'll have a 2 over 2y, so we have plus 1 over y delta y. What good is that? Well, we can rearrange this. We can say we have negative 2 times delta x over x plus 1 times delta y over y. Now what's delta x over x? That's 11%. 4 over 36, 0.4 over 3.6 is 0.11. So that this delta x over x is 0.11. That's our uncertainty, proportional uncertainty in x convertible to an 11% uncertainty. And here at 6.6, I'll say that's 7. So that should be about 0.07. So we have -2 times this plus this. Now the delta x over x could be a plus or minus 11. This could be a plus or minus 0.07 because remember our uncertainty can go either way. This result, and let's put absolute value signs around everything to get the magnitude of the uncertainty. The magnitude of this uncertainty is less than or equal to 2 times 0.11 plus 0.07. Now that is 0.29. Now really our delta f over f should have come out closer to this. As a matter of fact, it should have come out to 29%. We only got actually a little under 20%. Again, leading me to suspect that there's some kind of at least a minor error in the calculations, and of course you can figure that out. But this was observed to be 20%, 0.20, question mark, exclamation point, because it doesn't agree with this. And I'm going to point out, and you can confirm if you wish, that our general rule that errors propagate in such a way that if you have multiplications or divisions, you add the percent errors, so that we have a percent error in y of about 7%, a percent error in x of 11%, and we divide by x twice, so that 11% is going to count twice, so that our 7 and 11% uncertainties should combine to give us about a 29% uncertainty. The form of our differential for this function confirms that. We have a double of our delta x over x, a doubling of our x uncertainty. Because we have an x squared, we're dividing by x squared, which means we're dividing by x twice. And we have our y uncertainty. The y uncertainty only occurs once because we only multiply once by y. Again, I'm not going to give you all the detailed reasons for these connections and why this does work generally. Something you should be able to work out for yourself from this point. And whether or not you can work it out yourself, this should give you some validation and some insight into that rule for propagation of errors.